Shall we do it? We're recording this, right?
Yes, Zach is recording this as we speak.
Okay, so we're ready to go. All right, I think we should probably get started. We're very happy this week to welcome Professor Nikita Blinov to our seminar. Nikita did his PhD at UBC, and then did postdocs at Fermilab, Slack, and then a short stint at U Victoria as a postdoc before becoming a faculty member at York University. And today he's going to tell us about a really small scale structure, dark matter.
Thanks a lot for the introduction. I was at UVic for a normal amount of time. I was 2 years.
2 years,
Yeah. It was kind of in the middle of a pandemic, so it felt like, I don't know, a time warp, but anyway, yeah. So this talk is based on a bunch of work that I've done in the last few years with a few people, Patrick Draper, Matt Dolan, Jonathan Kozacek, Jesse Shelton, Barenboim, and Albert Stebbins, as well as some recent and ongoing work with Christiana Sampaio, who was a undergrad with me in the summer, sponsored by McDonald. So thank you for giving me money so I can give it to him. And then with Jesse Shelton, Josh Foster, and Ben Lemon. So a lot of this talk will be kind of based on these older papers with some new stuff involving these people later on that's unpublished and highly in progress. Okay, so the setup for this talk is that I want to ask about what does dark matter look like on really, really small scales. So what do I mean by this? So one way to capture a distribution of dark matter precisely in our universe is to look at the matter power spectrum, which shows the amplitude of matter fluctuations on the y-axis here as a function of their inverse size and impact. So inverse size means that large values of its axis correspond to really small scale, small values correspond to really large scales. So you can see that all the data points we have that summarizes our observational knowledge of the dark matter distribution in our universe occur at large scales. So these are scales of order the size of the universe, the size of galaxy clusters and galactic scales. And then nothing. So we don't know anything about the dark matter distribution at small scales. What we do know, however, fits extremely well with observation. So this is the standard cold dark matter model. This is the gray line which passes beautifully through all of the data. The current state of the art stops roughly at sub-galactic scales, which can be probed with a variety of ways using gravitational lensing, astrometric searches, as well as Milky Way satellite counts, as well as many other probes. So in this probe, or in this talk, I want to go way, way past the current state of the art observationally and talk about what happens at really small scales. So substellar mass dark matter objects that occur all the way here. So it's many orders of magnitude above what we can currently probe. However, this can hide a lot of interesting physics. Namely, I'll focus on two different examples. So to show that you can actually encode fundamental physics within these scales. Well, that got messed up. So you can squint. This is a plot of a galactic rotation curve.
Promise the small scale structure.
Yes. So this is why sharing a PDF is always preferable to doing this. So this is the rotation curve as a function of radius, and I think it's for the M33 galaxy. What I wanted to highlight basically is that the smallest scales on which we have probed dark matter, which allows us to fit this rotation curve perfectly, is like kiloparsec scales. So these are these data points are roughly kiloparsecs apart. So we kind of have a good idea of how dark matter is distributed on kiloparsec scales. So that gives rise to this picture of what the dark matter distribution looks like within a certain galaxy. So we have a big dark matter halo, maybe being orbited by dwarf galaxies, satellite galaxies, and such. So the end goal of this talk is to show that if we consider scenarios of dark matter physics and cosmological evolution, but slightly different from usual assumptions, we can end up with a very different picture of where the dark matter halo is not smooth, but rather very clumpy, made up of a bunch of substructures, which are little blue clumps. They're not to scale. I'll give two different examples of how this occurs, namely using early matter domination. I know many of you are familiar with this scenario, so hopefully this will be either boring or a fun review. And the second mechanism is using inflationary production of vector particles.
I just confirm, like your clumps here are completely in spatial coordinates, not fixed-dimensional, like they say.
I mean, if you have a gravitationally bound structure, I would assume if you were to plot the entire phase space, they would look coherent in phase space as well. But that's a good question. I haven't thought about what it looks like.
Just the way we find these microhalos in simulations is we do usually use 6D
Okay.
rather than 3D.
Yeah, that's a good question. So these, as you'll see, these are much smaller than what is traditionally found in standard n-body simulation. So that's one of the conclusions of this talk, is that to make reliable predictions for these scales, you need to do different kinds of simulations, which people are kind of starting to do, but you can't do like a big box n-body simulation starting from like initial conditions and simulate the whole universe. So you need to kind of zero in on these small scale structures. But I think the halo finding algorithms will probably work the same, just on a much smaller scale. So if you're using this 6D information, then it'll work in this case as well. So the goal is to go from some fundamental physics to dark matter substructure at small scales. You can think of this as happening in 3 different steps. So the first step is to set out some initial condition, which are the primordial power spectrum. So some distribution of dark matter and baryons and radiation in the universe. These initial perturbations evolve with time, and then finally, eventually, when they get dense enough, they will collapse to form structures. So, in principle, dynamics that give rise to non-trivial small-scale structure can arise at any of these steps. The 2 examples that I'll give focus on the first and a second step. So, let's start with the initial conditions. So, the minimal models of inflation, namely slow roll, single field inflation, predicts a nearly scale invariant power spectrum. So this is a power spectrum, the dimensionless power spectrum as a function of k, so the inverse distance scale. Simple models of inflations predict that the power spectrum is basically scale invariant, and CMB tells us what the amplitude of this power spectrum is. So it's quite small and very flat. These minimal models also tell us that the spatial distributions of dark matter, baryons, and radiation are all correlated, namely, they all have the same magnitude and are distributed in space in a similar way. So these sets of initial conditions, they're called adiabatic initial conditions. And these are observed on large scales by cosmological observations, like the cosmic microwave background. However, if dark matter is a light state that's present during inflation, this means that it can undergo its own fluctuations that are independent of inflaton fluctuations. And the result of this is that the spatial distribution of a dark matter is no longer correlated with the baryons and radiation. So pictorially, you can think of standard model stuff being spatially separated from a dark matter stuff. So one nice model in which this happens is a minimally coupled scale vector field. So this is a vector field with a mass. Minimal coupling just means that the only coupling to gravity occurs through square root of g. Non-minimal couplings would involve couplings to the Ricci scalar that would appear in the left hand. So we can take this model, run it through inflationary dynamics, use the equations of motion of the scalar field, and predict the power spectrum of this kind of dark matter candidate. And you find it has some non-trivial k dependence, so it rises at larger momenta or larger wave numbers. And it also depends crucially on the scale of inflation and the mass of your dark matter field. So this looks very different compared to the scale invariant power spectrum. So if this is a dark matter, if this vector is a dark matter candidate, then instead of this flat power spectrum here, that's predicted by minimal dark matter models, we get this huge enhancement at small scales. And where this enhancement happens is a function of the fundamental parameters of the model, namely the mass of the vector field. So in this sense, fundamental physics, particle physics is imprinted on the small scale structure. So that's how initial conditions can be modified to give rise to an enhancement of structure. The next step is to evolve this from these early times, so inflationary epoch, to late times when structure can form. So the evolution of dark matter perturbations just follows from essentially energy momentum conservation and gravitational physics, following from general relativity. You can write down the evolution equations for the dark matter density perturbations and combine them and simplify them in a fairly simple form. So this is the equation for dark matter density perturbation that depends on the following things. So first of all, its evolution depends on what the background universe is doing through the Hubble rate. It can depend on the local gravitational potentials. So these phi and psi are just elements of the metric that drive the evolution of dark matter densities. And then by the ellipses that represent all the complicated stuff of dark matter microphysics. So this can be complicated scale-dependent effects like radiation pressure, coupling to other species that prevent collapse of dark matter substructures. I'll mention a couple of these effects in a bit, but in principle, all of this could be captured by this equation. So this is a simple linear equation, at least while the perturbations are small. So you can solve this for different cosmologies, for different initial conditions. What one finds is that in matter domination, the density contrast of dark matter grows linearly with a scale factor, but in radiation domination, it grows logarithmically with a scale factor. So the usual assumption that before Big Bang nucleosynthesis, the universe was radiation dominated implies a certain rate of structure formation. So this means that before BBN, density contrast grew fairly slow. However, we have no direct observational evidence of the eras before Big Bang nucleosynthesis, so temperatures of a universe above, let's say, 5 MeV or so. So it's totally valid to consider other possibilities. One cosmology that's often considered is early matter domination. And you can see easily from this is that if our universe was matter dominated at some point, the dark matter contrast would grow much, much faster. Okay, that's not good. What should I do?
It's legible.
The problem is I spent a lot of time making these things look nice. Okay, look at it. We can draw stuff again. Okay,
Do you have like a different kind of is it on Keynote? The PDF?
Yeah, it's I have a PDF of this. The one time I wanted to show a video.
We can switch back to the video.
Yeah, well, it might get shrunk to like 2 pixels and then be completely useless.
Probably just play it not in presentation mode.
Well, okay. Here is that like the rotation curve. Very nice. Okay, here's the plot that I want to show. So I'm trying to argue that early matter domination, or basically any period of non-radiation domination at early times, is completely generic. The reason why is because if you compare the evolution, the time evolution of the density of some species X compared to radiation, which is thought to be the dominant component at early times, this depends on the equation of state of this extra component X. So if this has a sufficiently low equation of state, so less than a third, you can see that this will grow as a function of time. So for example, if X is some heavy stable matter with Wx equal to 0, this will grow linearly as a function of time, which means generically, if you have some new species, it will come to dominate the energy constant of the universe. So this is what this plot shows. So we have a scale factor or time on the x-axis and the ratio of some new species phi compared to radiation. So even if phi was initially subdominant, but because it evolved non-relativistically compared to radiation, its density increases linearly, and it comes to dominate the universe. And if it's sufficiently long-lived, the domination will continue for some amount of time until phi decays back into radiation and you get back to radiation. So the period, the epoch when this happens, when you return back to radiation, is called reheating, and it's denoted by attempted heat. So this is something that's been studied for a long time, especially in the context of string theory and supersymmetry, just because those theories have a ton of extra particles that are heavy, weakly interacting, that can do precisely this sort of thing. But it's also just interesting from the point of view of a generic possibility for a cosmological history that's compatible with data. So what does dark matter contrast evolution look like when you have a period of early matter domination? So this is showing the evolution of a mode of particular size that enters the horizon before reheating. So it experiences some of the enhancement due to early matter domination. So this is the horizon entry, and then you can see this period during early matter domination corresponds to linear growth of the density contrast with the scale factor. And then when reheating happens, you transition to radiation era, where the growth continues, but only logarithmically. So the end result is that for these modes, you get this factor of enhancement in your density contrast, which is roughly the scale factor at reheating over the scale factor at which the mode entered the horizon. And this can be a large number. So I've mentioned that generally microphysical models of dark matter have these complicated terms that encode microphysics, like coupling to radiation or wave effects. So this means that this linear growth happens, not at all scales, but at all scales where dark matter behaves as a cold dark matter component with an equation of state equal to 0, so no pressure. However, many microphysical models of dark matter, that's not always the case. Like, for example, even in thermal whips, there's some kinetic equilibrium, some kinetic coupling of the dark matter particles to a radiation bath, which means that certain modes grow linearly, while others are pressure supported. They can't collapse because they're interacting with radiation, which pushes the overdensities outwards. So this plot is showing the density contrast of some dark matter modes as a function of conformal time, but think of this as just something that's related to the scale factor. This isn't for early matter domination, but this just shows that certain modes of certain sizes grow while others oscillate or even decay. And that depends on basically on when they kinetically decouple from the plasma with which they're interacting. Similarly, for other dark matter candidates like axion-like particles, which are oscillating scalar fields, they only look like cold dark matter on large scales. On small scales, the fields are oscillating, which means that pressure and radiation and density are also oscillating, which can be described as an effect of sound speed. So this again means that certain perturbations don't grow as fast as you would expect. So this plot again shows the evolution of a density contrast of an axion-like particle as a function of a scale factor for a few different choices in modes. So some of these are growing like cold dark matter would. But this corresponds to something for which these effective sound speed effects are important. And you can see that it starts out to grow, but then basically starts to oscillate and decay precisely because it can collapse due to these oscillatory effects kicking in. Yeah.
Can I just ask a basic understanding question about that? So normally when I think about axions and axion-like particles, particles fairly weakly coupled to themselves, or maybe I'm just thinking about piece of the axion here. So does this sound speed effect, does it require that the axion-like particle have a substantial?
No, this is everything I'm going to talk about is gravity only. The sound speed effect. Remember the sound speed is related to pressure over density, right? So for a scalar field, the pressure is like 1/2 pi dot squared minus like 1/2 m squared pi squared, something like that. So phi is something that's oscillating, so this pressure will also oscillate in general. So you can describe these oscillations in terms of an effective sound speed.
Okay, so typically when you use that description, you're using it to prove that, it's like pressureless, so it evolved over a long amount of time, but you're saying as it's coming into the horizon, that's not the case, and so there's actually some
Yeah, so it depends on the length scale of the mode you're talking about. So if the mode is comparable to, let's say, the mass times the scale factor at horizon entry, I think, then these oscillatory effects become important. Yeah, so this is exactly, so this line actually comes from solving like the full field equations and computing the pressure and this way. So this is actually computing the density contrast from first principles using equations of motion of the fields. And this is some of these compare that sort of evolution with using this effective equation for density contrast with just a sound speed. So depending on your K, the wave number you're interested in, these effects can be important or not important.
and it comes from the fact that the horizon entry is happening sort of at the
So
not much.
these modes are chosen such that this mode is really affected by these effects. This mode is not really affected, and these ones are not affected at all. So there's precisely to illustrate this kind of effect, wave number dependent effect. Yeah, so in short, you can think of this as a wave number dependent sound speed, which vanishes when the wave number is sufficiently big, which means that it's much larger than, sorry, much smaller than m.
At which point you can oscillations on small scales that average out. But yeah.
Exactly. Yeah. Okay, so that's all to say that some modes will grow, other modes won't grow. You can summarize this by constructing a power spectrum again. So this is now a power spectrum corresponding to different models generated by early matter domination. So this is just showing two EMD models for two different reheating temperatures. So one reheating at 5 MeV, which is basically the lowest temperature was compatible with observations and things like this. One with 100 MeV, and basically modeled this complicated wave effect by just putting a sharp cutoff at a value that corresponds to the mass. So it's mass dependent effect. The smaller the masses are, so that corresponds to longer Compton wavelengths, that corresponds to wave effects kicking in at larger physical scale. So it's smaller than response. So this is 10 to minus 90, this is 10 to minus 80. So you can see this provide the cutoff. This is just a simplification. Of course, the actual cutoff would be something smooth and probably oscillatory, but this is just a crutch basically to make calculations easy. The upshot is that in these models with early matter domination, you get a big enhancement in the power spectrum with small scales, just like in models of inflationary dark matter production with vector dark matter. So this plot shows a similar example, but this is just cold dark matter. But I wanted to illustrate this because here there's another cutoff that looks a little bit different. And this cutoff comes from the fact that if early matter domination lasts long enough, then you will have structure formation during the early matter domination. So this is something that you've considered in your model, right? So those structures, barring any other interactions, will get disrupted when early matter domination ends. So this gives rise to a cutoff which is from gravitational effects alone. And I think if I understand your work correctly, then this is why you needed your strong self interactions to make sure that you collapse into dense enough structures to survive this period, right? So if you don't include those self interactions, you get a kind of a model independent cutoff just from the fact that these structures that form early enough, they blow up when reheating happens and kind of drag along dark matter, washing out structure at early times. So this is to say that the power spectrum really can contain a lot of physics, contain physics about the cosmological evolution. The slope here depends on the equation of state of the universe when this enhancement happened. where the cutoff happens depends on the dark matter mass, the physics that give rise to the cutoff, and so on. So this is a really an interesting object to study. Okay, I've mentioned all these things. So now we're on to step 3. We will have an initial power spectrum. So initial here means, let's say, at temperatures of order 5 MeV. We want to evolve it forward, see what happens. So of course, when you let gravity do its work, the overdensities will become more and more overdense until eventually they begin to self-gravitate and collapse into objects that decouple from the Hubble expansion. So that's, we say that forms structure. So because our power spectra at small scales is so enhanced compared to the expectation from extrapolating the usual power spectrum that's measured by the CMB, this collapse happens much earlier in these models with enhanced structure. So in order to describe the objects that are left over at the end of this collapse, you need to have some way of dealing with the fact that when the collapse happens, things are nonlinear. Everything I've mentioned so far has been physics, linear physics. So one correct way to do this is to do n-body simulations, which is hard because the length scale, or one of the many reasons, is that the length scale of these objects we're talking about is very, very small. So you'll see that they correspond to dark matter halos that are hundreds, thousands of astronomical units, which is much smaller than the resolution of kind of state-of-the-art n-body simulations that evolve, that study galactic evolution over cosmological times. So this is just a qualitatively different regime which you need to explore. So what I opted to do was to use semi-analytics. There's a theory called the press-structure theory that allows us to basically use the linear results to predict various things about the substructure, namely when collapse happens, the distribution of dark matter halos. The challenge is that, well, press-structure has been tested and tuned to large-scale dark matter halos, precisely by comparing to simulations. This hasn't been done for the small-scale stuff we're talking about. So we're kind of, there's a bit of guesswork involved here. So it'll be really nice to have some kind of simulations to tune these semi-analytic models. So one thing that we can compute using this press-structure formalism is the time of the collapse of different structures. So this plot is showing the typical mass scale. I'm sorry, but collapses at a given redshift. So early times corresponds to the right-hand side here, and late times corresponds to the left-hand. So these different lines correspond to different models. So we talked about early matter domination and the vector dark matter generated by inflation. And this standard cosmology is shown here. So in standard cosmology, where you start off with density perturbations that are of order like 10⁻⁵, it takes a long time for them to get to a size big enough that they can begin to collapse and decouple from Hubble flow. So this is just this effect. Nothing happens in the standard cosmology until redshifts of order 20. So, but then everything happens almost instantaneously. So a lot of things start collapsing. Basically, all scales go nonlinear, which is why you need to do n-body simulations. In models with enhanced power spectrum, something qualitatively different happens, right? So here, because we had start off with such a large density contrast at small scales, collapse happens basically at matter radiation equality. So at Z of order 3400, and then it continues. So different masses collapse at different times. So as you go later and later times, you can see that bigger and bigger masses, mass objects form. And for this, we conclude that structure forms hierarchically. So you merge, initially small clumps form, they merge into bigger clumps, bigger and bigger clumps, and so on. So this is a picture of a simulation that Eric Chick and Wallstein did. I don't think this is a published work, but this is the only simulation of a formation of a mini halo that I found. And you can kind of see the substructure, the hierarchical nature of this process, right? So this clump that's supposed to be of order like an Earth mass is made up of smaller things, which are made up of smaller things. Okay, so another useful thing we can do using press-structure is estimate the density and size of these objects, which is something that's really useful for detection, of course. The density of these objects depends very strongly on when they form, when the collapse happens. So you can estimate that if collapse happens at Z of 100, then you have a big density. So remember that the local density of dark matter at the solar radius is expected to be about 0.3 G per centimeter cube on average. So this is much larger than that. So you have significant density enhancements within these mini halos. You can also estimate their size just by knowing the mass and their density, right? So for the EMG model, the size, like, it varies, depends on the collapse, depending on the collapse time and on the reaching temperature. But it's somewhere in the order of, you know, tens, hundreds, thousands of astronomical units. So these things are dense, but they're not extremely dense. They're small, but they're not extremely small. So they're kind of fluffy balls of dark matter of order the size of the solar system. And here's a shout out to you all, because this assumes only gravitational interactions. And of course, if you start including other interactions, you can get wildly different numbers. Okay, so we get this picture that in very simple, reasonable models of dark matter and cosmological evolution, you get a very different idea of what the dark matter halo, let's say in our galaxy, looks like. Instead of having a smooth distribution, it's made up of many small scale clumps. So there's another effect of early matter domination that I just want to mention briefly, is that for direct detection purposes, having this period of early matter domination changes significantly the parameter space that you might be interested in. So this plot shows the axion-like particle case with the coupling photons on the y-axis and the mass on the x-axis. These different bands correspond to different predictions of the parameter space that's favored in different scenarios. So this is QCD axion, this is the standard cosmology for an axion-like particle that's not necessarily tied to QCD, and this is early matter domination. So your experiments are trying to reach these different targets. You can see that early matter domination is kind of like the most pessimistic one, the hardest to reach. Something similar happens for WIMP dark matter. So this is a complicated plot, but I just want to mention that for normal dark matter annihilating just channel particles, the cross sections for which you obtain the correct relic abundance are of order 3 × 10⁻26 centimeters cubed per second. For models with early matter domination, the cross sections for which you get the right relic abundance can be much smaller. The reason for that is very simple, because when the period of early matter domination ends, you do a huge entropy dump into your plasma, which dilutes all the densities, which means to get the right relic abundance at late times, you would have needed to overproduce dark matter, which means you would have needed to froze out earlier, which means a weaker cross section. So these cosmologies have an effect not only on kind of the spatial distribution of dark matter, but also on detection prospects and with Earth-based experiments. So let me just mention some of these prospects very briefly. So the fact that dark matter is clumpy has profound implications for direct detection, for example. You have to wait. If dark matter all of it is bound up in these clumps, and we've had a nice discussion about, but maybe that's not necessarily a good assumption after a long cosmological evolution. But if it is the case, then you basically have to wait for your clump or your detector to run into a clump of dark matter, which for a given size and mass of clump, you can estimate how long that takes, and it's much longer than the span of a PhD thesis. So not a great strategy, maybe. But again, this is assuming everything is in these clumps, which is not necessarily a good assumption, because when hierarchical structure formation happens, the clumps encounter each other, they disrupt each other. Clumps can run into stars, which tidally disrupt them. So some of the dark matter that's initially bound in substructure can get liberated and become free-floating, which would be detectable with the direct detection experiments. So this has maybe bad use for direct detection, but for indirect detection, this can actually be a boon, because in direct detection, the signals you expect to see, they scale with a square of the density of dark matter that's annihilating, right? So if your density is thousands of times higher inside of these structures, it means that your rates for annihilation get enhanced by millions. But these things depend on kind of a microphysics, right? So they're very sensitive to cutoffs. So that's all to say that if we want to test for the presence of these clumps in the dark matter distribution robustly, we should probably think of gravitational strategies for detecting them. So probes that don't make use of any coupling to standard model particles. So that's what I want to talk about for the rest of the talk. Okay, so this is a bit of an equation dump, but let me just remind you of the mass scale and the size scale of these clumps. I picked the equations corresponding to early matter domination, just to highlight the fact that we're talking about mass scales for dark matter halos that are less than tens of Earth masses, and sizes that are tens of AU, hundreds of AU, thousands of AU. So these are very light masses and very large sizes if we're talking about gravitational ways of probing these things. So the typical things that come to mind whenever you think about gravitational probes is just like, okay, maybe I can do something with strong gravitational lensing. Then you take this mass, you compute, take this mass, take this size, compute the Einstein radius for this object. The Einstein radius is something that grows with the distance to the lens. So if you put your lens at a gigaparsec, then the Einstein radius is 0.1 of an astronomical unit. To make use of such a small lens, you would need a source that fits inside of the Einstein radius. And there are basically no sources that you can see at such large distances that have this small of a size. So strong gravitational lensing by individual clumps is a no-go. There are other gravitational effects, though, that seem a bit more promising. So one is Shapiro time delay. So if you have some source, like a fast radio burst that emits a radio burst, this will pass by a bunch of substructure, and it will experience a gravitational time delay called the Shapiro time delay. And depending on the line of sight of a source, the signal will pass by slightly different substructures. So you'll have different shifts to the arrival times of your signal. And the effect is tiny. So for Earth mass subhalos, you get shifts that are fractions of a nanosecond. This has recently been studied in this paper, and the claim is that this is potentially detectable with future observations of fast radio bursts with a very futuristic setup where you have, basically telescopes that are like an AU apart. So this is something futuristic mission in space, but in principle, the numbers seem to work out. Another possibility that's been studied fairly extensively in the literature is using pulsar timing. So the idea there is very similar. If a pulsar gets yanked on by a mini halo, it will induce a Doppler shift to the pulses that it's sending out. So you can predict what the phase shift and the arrival times of this pulse is. It depends on the mass scale, the relative velocity, and gravitational coupling. And again, you plug in numbers, you get numbers of order a nanosecond, which is very small, but people have argued that by monitoring hundreds of pulsars over decades, you can potentially reach these kinds of sensitivities and possibly probe these mass scales. Hmm? Oh, sorry.
Oh, yeah, I do have
Okay.
I was also scratching my head. Say a little bit more about the FRBs. What exactly is giving you this evolution? Is it a difference in the shifting of frequency, like the frequency based effect?
So
FRB fold?
I'm gonna try to reconstruct this paper.
Okay.
So let's say you have two satellites observing an FRB. I don't know what it looks like. Let's imagine it looks like this. So, and you have dark matter substructures in the middle, right? So if the same FRB is observed by two different lines of sight, this line of sight will experience slightly different time delays compared to this line of sight. In fact, there'll be some kind of a statistical noise on the relative arrival times of the FRB, but you can predict based on the number distribution, the density of clumps, and so on. So
So multiple separate.
yeah, so you need, I think you need at least two, and they need to be separated by sufficiently far away, but the lines of sight are sufficiently different. Yeah. Okay, so these things are very cool, and these seem promising, but maybe a little bit futuristic. Let me talk about my favorite potential probe, which involves using collective effects of clumps, which is kind of similar to this. So let's assume that most of the dark matter is in mini halos. We can ask about the effect of a distribution of these clumps on lensing observables. So in gravitational lensing, we define the convergence as the integral of the dark matter density along a line of sight. We can decompose this convergence into some smooth component and fluctuations, meaning that, again, going back to this picture, different lines of sight will contain slightly different amounts of dark matter because they will pass different impact parameters to dark matter substructure. So the convergence, this integral along a line of sight, will differ slightly between different lines of sight. So this difference is encoded by this delta kappa. So sigma critical is the critical surface density of the lens, which basically says that if kappa is of order 1, then you expect strong gravitational effects. Delta kappa will be very small, so you don't expect strong gravitational effects from delta kappa alone. So you can ask, well, how many clumps are actually along a line of sight? So given their size and their mass, you can compute roughly how many of them are there, and you find that there could be hundreds, thousands, tens, depending on the parameters. It just depends. Just to reiterate the same point, this means that different lines of sight will have potentially different dark matter densities, different convergences, which is something you can potentially leverage in gravitational lensing. You can predict the statistical properties of these convergence fluctuations just because you can compute the distribution using this perspective formalism. You can make a guess about what their density profile is. And the power spectrum of these convergence fluctuations looks like this. So this is the mass function, so the distribution of the mini halos is a function of mass times the Fourier transform squared of the density profile. So the main point is that the physical size of these convergence fluctuations, projected density fluctuations, goes like the dimensionless power spectrum. So you can compute this for a few different models. So this is taking some very massive halos to be of order Earth mass with different concentration parameters. This is just to illustrate that this is something you can compute. At a typical size, like the maximum size of fluctuations that you expect for reasonable choice of parameters, is like -3 to -2. So the convergence fluctuations are very, very small. And remember, to get strong effects, you need kappa to be of order 1. So you don't expect strong effects just from the fluctuations alone. So something special needs to happen. So let me take a brief aside and tell you about lensing, gravitational lensing next to a critical line. So in gravitational lensing, we're interested in relating source frame coordinates to lens or image plane coordinates via some gravitational deflection. So this is the setup. We have some observer observing a source through a lens. So the data here is the direction to a position on the source plane. Data is the direction to position on the lens plane. And they're related by a gravitational deflection alpha, which is related to basically to the gravitational potential of the lens. If you're interested in a very small scale effects, you can basically Taylor expand this map and find it's approximately equal to this locally. So here, kappa and gamma are different derivatives of the lensing potential, which is related to the gravitational potential of the lens. The magnification for a given lens is then given by the inverse determinant of this map. So it has this So you can see that if one of these eigenvalues vanishes, the magnification blows up, right? Let's say this eigenvalue vanishes. So this condition is satisfied. This means that for certain extended lenses, there are special regions called critical lines in the lens plane or caustics in the source plane, along which the magnification of the point source is formally infinite. But something interesting happens there. Let's say instead of just smooth convergence kappa, we have our small fluctuations delta kappa. And delta kappa is small. If we expand this expression in terms of delta kappa, we find the following for magnification. So we have our smooth component, mu, times 1 plus delta kappa, which is small, but it's multiplied by a large magnification. So this just says that when this thing is close to 0, the size of the magnification is very sensitive to small shifts away from 0. So this means if we have a system where the magnification is huge, that multiplies delta kappa, you can get order 1 changes in the magnification along different lines of sight. So they can be potentially observable. So let me just summarize. We are interested in finding systems where we have very large magnifications, such that this correction to the magnification can be of order 1. So this means that mu has to be pretty big, such that when it multiplies delta kappa, it gives you something of order 1. And you need sources small enough such that the magnifications can actually reach these large numbers, right? So remember, delta kappa was something of order 10 to the -3. This means that mu has to be 10 to the 3, so a very large magnification. It turns out that the maximum magnification of real sources is related to their size. The smaller the source, the larger the potential magnification. So in fact, it goes like the inverse square root. So if you want to reach really large magnifications, like 10 to the 3, 10 to the 3, the sources have to be small. They can't be like a quasar, like something that's enormous. It has to be something much smaller. Okay, so the cool thing is that such systems exist where magnification is really big. So here's a picture of a galaxy cluster called MAX J1149.5. So in white here, this is the prediction for this critical line for a particular model of this galaxy cluster. You can see that straddling the critical line, you have 1, 2 images of a background galaxy. So this is exactly where strong lensing happens, right? So even more exciting is that the sources of the kinds that I described apparently exist. This is just recently observed in 2017. People have been able to see individual extragalactic stars. So this is a star at redshift 1.5 that's being magnified by a cluster at redshift 0.5 or something. So it's actually the same cluster. So remember, I was showing 2 images of this background galaxy. We're zeroing in now on the critical line. And if you can squint, there's 2 little tiny blobs here, right next to the critical line, which are first observations of an extragalactic star. So this is a single star at a distance of 2 gigaparsecs. This is insanely far away. The reason why people think it's a star is they can measure its spectrum and confirm that its spectral density matches that of a particular kind of star called a blue supergiant. So it's not some dim, pinky star. It's an enormous, really bright star, but it's extremely far away. So knowing what we know about blue supergiants, you can basically deduce that the star would have been magnified by a factor of more than 2,000 in order to have been observed in this way. So this is the first observation, but in the last few years, there's been many such observations of stars at even bigger redshifts. And people have started making catalogs of such highly magnified individual stars. And people are interested in these for completely unrelated reasons, for studying, early universe stars and things like that. But we can leverage this for looking at dark matter substructure. So here's the full scheme. So the way that people observe these highly magnified stars so far is in difference imaging. So you take a picture of a near caustic region, a near critical line region at one time, and then at another time. Normally, the star is too dim to be seen, but sometimes if you take a difference of those two images, something shows up. What this means is that basically the star got brighter above a certain threshold, such it could have been detected. And the reason for these time-dependent brightness enhancements is microlensing. So some compact object in the lens, in the like macroscopic lens in a galaxy cluster, moved in front of a line of sight to the star and briefly enhanced its brightness, such that it could have been observed. So because the baseline magnification is so high, because of the cluster, because of proximity to the cluster caustic, this means that tiny density fluctuations due to microhalos they can be seen in the light curve of these highly magnified stars as they are undergoing a microlensing event. So this is something that was first studied by Dai and their own yesterday. They basically provided an estimate saying that if delta kappa is an order 1 over magnification, we get order 1 brightness fluctuation. So based on observed magnifications, this means they're potentially sensitive to delta kappa fluctuations of order 10 to minus 3, just like we've seen predicted by certain models of dark matter substructure. So here's what this looks like pictorially. This is from Dai and Escoudet's paper. This is showing magnification as a function of time. So if we focus on the gray line here, this is the microlensing magnification in absence of substructure. So it's something's moved. And then if you have substructure on top of it, you get these statistical fluctuations as the star, as the lensing happens, the star moves relative to dark matter. So the effective line of sight to the observer changes. They're sweeping across these different density fluctuations. So delta kappa is moving, the magnification changes by order 1. Okay, so basically using this as an estimate, we can deduce what kinds of dark matter substructures we can be sensitive to. So this plot shows the dark matter density, the typical clump density and solar masses per parsec cubed versus clump mass. So a given dark matter model, so a cosmological model or so early matter domination or things like inflationary vector production, they can give us a line in this space just by using this projector mechanism. So they can relate the mass scale to the density or the density to the size. So you can relate those things and basically plot a line. So this green shaded region corresponds to parameter space that's potentially favored by these kinds of models. And this region that's above these pink lines is something that can be probed potentially by observations of this kind. So if you're sensitive to order 1 fluctuations in the magnification of these highly magnified extragalactic stars, where the maximum magnification is of order 10 to minus 3, you can probe these mass scale, which correspond to certain mass scale. So the cool thing is, the thing that got me interested in this originally is that the sensitivity region, just at the tilde level estimate, passes right through a bunch of this parameter space. So this is a very basic estimate. The question that I'm trying to look at now is basically, can we do better? Just because this appears to be so promising. The questions are really basic. So we don't know what kind of an observational program is needed. What kind of instruments? Can we use current instruments? How often do we make these observations? What kind of systems do we study? For how long? Are these observations even potentially sensitive to dark matter microphysics? So I mentioned that the power spectra are sensitive to things like reheating temperature, the dark matter equation of state, the equation of state of the universe when the dark matter structures grew. So these parameters are all buried in the predictions of the microhalo properties. Can we extract them from these fluctuations of the lensing magnifications? So how do we do this? Well, we basically need to model lenses, and we need to be able to model fluctuations due to dark matter. Fortunately, this turns out to be somewhat easy, right? So remember that we're talking about a very specific region in the lens that's very close to a critical line. So we're not talking about really complicated global properties of the lens of a galaxy cluster, which is shown by these different colors here, different lines correspond to different lens models, so you can see that they can differ significantly. But wherever lensing is the strongest along the critical lines, all the models agree. And moreover, the critical lines look really simple there. They basically look like straight lines because you're able to essentially tailor expand the lens map in the vicinity of a critical line. So this means that I switch notation. This is like the source plane coordinate. This is just a generic expression for lens map. I'm saying that we can expand this in the vicinity of the critical curve and just get them polynomial. So this is still a nonlinear map that maps our lens plane coordinates to a source plane, which we need to invert to find magnifications. But this is much simpler than it would be otherwise. So we can simulate this. We can kind of compute what the lens map looks like. So it's just an illustration of the left-hand side of this equation. It's showing the lens plane coordinates just to show if it's smooth, if you just don't include any substructure. And then on top of this, we can add fluctuations and convergence, which end up as fluctuations of gravitational deflections. So this is a kind of a Gaussian random noise that's generated for a particular power spectrum motivated by dark matter models. So note that I'm just going to highlight the size scale. So this is the smooth component. This is the small fluctuations that are of order 10⁻³ compared to the smooth component. From this lens equation, we can compute the magnification. So if you ignore the fluctuations, the magnification is smooth, and it's in this plane, in the source plane. So yeah, the lens plane, it's just a straight line because we're again zeroing in on the very particular region of the galaxy cluster lens. But if we add fluctuations, small fluctuations, right? These are tiny fluctuations. They completely disrupt the smooth magnification into something clumpy. This is exactly why when a source transits this region, the magnification changes by order 1, even though initial density fluctuations are very small. Somehow the large magnification of the cluster is enhancing the small scale fluctuations due to dark matter microhalos. Okay, so this is the thing that I want to show as a video. I don't know if this is going to work, but let's see. So this is the work that I did with Christiana, who was the McDonald Institute sponsored undergraduate. Okay, this is, let's see.